In this work, we present the DNA rendering dataset, which is a large-scale, high-quality, and high-fidelity dataset for human-centric rendering. Realistic human-centric rendering is an essential topic in computer vision and computer graphics communities. However, the vacancy for a comprehensive dataset to train or evaluate related algorithms is still there. Given the importance of the dataset's quality and diversity, we propose DNA rendering to address this gap and accelerate research in human-centric rendering. To achieve high-quality and high-fidelity data collection, we construct a professional multi-view system to capture data for DNA rendering, which contains 60 synchronous high-resolution cameras. An automatic pipeline is designed to generate comprehensive and accurate annotations for the dataset. To ensure data diversity, over 1,187 motions are designed for this dataset and are performed by 500 actors, including 153 professional actors and 347 normal actors. There are 1,500 sets of outfits from our clothing library with 527 daily clothing items and extra 153 special clothing sets. These widely distributed dimensions guarantee the diversity of our dataset in various aspects. DNA rendering dataset surpasses existing works in terms of variability and low bias. Our rigorous dataset design ensures that our dataset offers significant advantages over other works in multiple aspects. Specifically, DNA rendering provides video data including 500 by 3-person ID and outfit combinations, 1187 different motions, 60 camera views, and a total of 67.5 million frames. The resolution of our high-fidelity dataset is up to 4K. Further details will be provided in the next few minutes. We split the dataset based on the level of difficulties in 4 dimensions, which are motion, texture, deformation, and interaction. These are the 4 key factors that impact the rendering quality. The difficulty levels of each split are benchmarked by several representative human-centric state-of-the-art rendering works. Here we show the most representative data of each split along with the quantitative result of the novel view synthesis task. The content of DNA rendering is carefully designed to ensure a wide range of variations in motion, clothing, and human-object interactions while maintaining a balanced distribution across ethnicity, gender, and age. Our comprehensive dataset covers not only daily motions and clothing, but also professional skills, sports, traditional outfits, and special costumes. To achieve high fidelity, DNA rendering captures the sharp edges of sophisticated textures and accessories with 4096p resolution cameras. Besides intricate patterns, it also captures the unique reflectance effects of different clothing materials for realistic rendering. We invite the actors and actresses to perform selected actions in our specially designed capture system. Our capture system contains 60 high-resolution cameras, 8 Kinect cameras, and 16 lighting boards. These components are expertly arranged in a sphere with a radius of 3 meters. The video streams and depth streams are all synchronized, allowing further processing and data annotation. DNA rendering's comprehensive annotations include camera calibration, camera color calibration, image masks, key points, and SimpleX parametric models. Here shows our full annotation pipeline. We designed an automatic annotation pipeline for the mask, key points, and SimpleX parametric model annotation. Refinement and optimization modules are applied in each step for accurate and precise results. Based on the data capture system and annotation pipeline, DNA rendering provides high-resolution multi-view images, accurate multi-view image segmentation, and 2D 3D key points in COCO whole body format, which include face and hand annotations. Additionally, our dataset features SimpleX parametric model data for a comprehensive human annotation. Our capture system, automatic annotation pipeline, and manual quality check guarantee that each frame in DNA rendering is annotated accurately and meticulously. We benchmark DNA rendering on human-centric rendering tasks with state-of-the-art works. Novel view synthesis, novel pose animation, and novel identity rendering. We present both quantitative and qualitative results of each task. Also, we show the generalizability of our dataset compared to existing ones via a cross-dataset experiment. In the novel view synthesis task, we train the dynamic human rendering methods, namely neural volumes, ANORF, neural body, animatable nerve, and human nerve. Spirit models are trained with a dense 42 views on each action sequence. We evaluate the rendered image quality on 18 unseen testing camera views. We also report the quantitative results in PSNR, SSIM, and LPIPS of each method on 13 test splits. Please check out our technical report for an analysis of these results and a discussion on the conceptual differences among benchmark methods. In the novel pose animation task, we train the models of the same dynamic rendering methods on the first 80% of frames and evaluate novel pose rendering given human poses on the rest 20% of the frames. Similar to novel view synthesis, we also quantitatively compare the benchmark methods on rendering metrics, and our paper provides a thorough discussion on these results. We also benchmark 5 state-of-the-art generalizable NeRF methods on novel identity rendering. 3 category-agnostic methods, Pixel NeRF, IBR-Net and Vision NeRF, and other 2 human generalization methods, Neural Human Performer and Keypoint NeRF. We train these methods on 400 performances with balanced distribution across all dimensions and difficulties and evaluate the rendering quality on novel identities. Generally, the generalization methods with human prior outperform category-agnostic methods, especially when difficulty increases. Finally, we evaluate the effectiveness of the proposed dataset via cross-dataset evaluation. We compare DNA rendering to recent human-centric rendering datasets GeneBody, HuaMan, and ZJUMOCap. We train generalizable methods on the official training set and evaluate the performance of all datasets. We visualize the evaluation results with affinity matrices. The diagonal elements are in-domain results, and the off-diagonal elements reflect the robustness of the dataset trained models. Despite the domain gap, DNA rendering achieved the best rendering quality on other datasets without any fine-tuning. Please refer to our paper for detailed settings and additional results. With DNA rendering, high-quality human-centric rendering can be achieved, which has many potential applications, such as film and video game production and avatar generation. Moreover, by integrating human-centric rendering with scene rendering, it is possible to create more immersive and realistic virtual environments, which can be utilized in various fields, including VR, AR, and the construction of virtual communities. In summary, our work introduces DNA rendering, a multi-view dataset that is large-scale, high-quality, and high-fidelity, aiming to aid further research in human-centric rendering. Additionally, we compare it to existing datasets to verify its generalizability and offer benchmarks for 3 rendering tasks. For additional information and access to our data gallery, please refer to our project page.